Good morning all. For today's session, our title of the session is 3D printing of composites. We have already undergone a very exhaustive session by Professor Kumar on additive manufacturing, wherein we had a glimpse of all the 3D printing processes and technologies. So I will not go into that discussion, but I will directly focus on the 3D printing of composites. So this would be the outline of my presentation. We would initially talk about something about the traditional manufacturing processes of composites, and then we will have our discussion on 3D printing of fiber reinforced composites, polymer nano composites, polymer ceramic composites, and polymer metal composites, followed by the possible research avenues in the 3D printing of composites as on date. So this would be the outline of my discussion. As we know, composites are engineered or naturally occurring materials which are made from two or more constituent materials. Now these materials have significantly different properties, and when they are combined together as a single part, they remain separate and maintain their distinct identity at the microscopic level. However, with the combination of these two different materials, we get a new material which exhibits some of the finest properties of both the constituent materials. So such type of material is known as a composite. This differs from the alloys where we have multiple mixture of different elements. However, they mix evenly with each other in the microstructure, whereas that is not the situation in case of composites. If we see the applications of composites as on date, it ranges in wide number of fields, starting from textile and paper industry. This has wide applications in aerospace and aircraft industry, in automotive industry, in various civil engineering applications, in the fabrication of sports equipments, in the equipments for energy production. Portable power sources are also made up with the composite materials. The acoustic device, the body of acoustic devices like guitar are also nowadays made from composites instead of wood and timber. So there is a diverse field of applications where composites have replaced the traditional materials being used. Now, if we talk about traditional manufacturing processes for composite, the most elementary method is the hand layup technique. The hand layup technique is one where we prepare a mold initially and place the fabric into it, followed by the manual application of resin into it. Now, this is required to be very lengthy process, very tiresome process, and the curing also takes substantial time. Further, when such traditional method is used, we also often need secondary processes for proper curing and for proper finishing. So these processes, as such, hand layup technique based processes are very elementary and lengthy process. Against that, recently resin transfer molding processes, be it under pressure or be it under the effect of vacuum, this is also a leading process as on date. Here what happens is a mold is created and the fabric is placed into it, and then the resin is passed either under the effect of pressure or it is spread inside under the effect of vacuum. So this is how the resin transfer molding process works. In either of this process, as I said, we need some sort of post-processing like autoclaving and vacuum molding. Similarly, very highly skilled manpower is required, and because you have a lengthy process, you have more number of parts involved, the costs involved are also on the higher side. So fabricating composites by this traditional process makes them costlier when you compare them with the standard plastics and metals. So as against these traditional manufacturing processes, 3D printing as on date is becoming an alternative manufacturing method for composites. However, this works well when the production volumes are less or to the medium numbers, and when highly customizable parts are required. So in such cases where we need to carry out rapid prototyping for preparing the prototypes, or when we need to make personalized devices or structures which have usually the complex geometry and which probably may not be possible to be fabricated by even the traditional composite manufacturing processes, 3D printing comes as a handy tool to fabricate such components. Now, when I talk about the 3D printing of these composites, I would come to these 4 different types of composites, as I had initially said. We will have a discussion on how the fiber reinforced composites are produced. This would be in a greater detail, including the work which we are carrying out at our place. Then this would be followed by the nano composites using polymer matrix, followed by ceramic and metal composites under the polymer matrix. This would be the 4 different class of composites which I plan to discuss today. Now, when we try to fabricate fiber reinforced composites, the first type that I talked about, there are 4 out of these 8 methods which are being used for their fabrication. This being the most elementary being the FDM process, where a where a filament is used, the SLS process wherein photopolymerization of resin is carried out. Then we have laminated object manufacturing, LOM process, and finally we have the 4th process is the SLS process, wherein the powder is cured with the help of the lasers. So these are 4 basic 3D printing techniques which are being used for printing of fiber reinforced composites. Now, when we talk about the composites, fiber reinforced composites, especially using FDM process, here by and large carbon fiber and glass fiber are being used. They can be continuous fibers or they can be chopped fibers. However, when attempt is being made to print the filament with these fibers, either fibers mixed into the filament initially or filament being passed through the same nozzle along with filament, or the filament being passed through a separate nozzle along with the deposition of this filament. In either of the case, one major issue that comes up is the nozzle clogging, because the polymer that we might use, be it nylon or PLA or ABS, that works at temperature somewhere around say 180 to 210 degrees Celsius, and these fibers have very high melting point. So usually they remain intact as it is, and they create some sort of disturbances while the extrusion of this part is carried out through the nozzle. So that results initially into some sort of wear, and at some point of time when the percentage concentration of these fibers is relatively higher, then there are chances that the flow is hindered from the nozzle opening and resulting into clogging of such nozzles. Further, the high fiber that we may have, the high concentration of these fibers will weaken the interlayer fusion between the parts. So when the part is printed and when the layers are deposited in case of FDM, the fusion between the interlayers slightly gets weakened with the help of because of the higher proportion of fiber, and so that would result into lower interlaminar shear strength. So overall the part becomes weak if the fiber proportion is higher. So usually the proportion of fiber along with the selected polymer is usually maintained at a lower value. However, depending on the type of polymer, depending on the type of fiber, we may have to work on the proportion, and this also can vary based on machine to machine. So sometimes the proportion that we find out optimum and effective for one machine, that may not work for another machine. So for as far as industrial application is concerned, there is a requirement to have proper parametric investigation of a new machine. And here there is an opportunity for MTech or PhD students to work with some industries who use these machines for mass production. So there they would need to optimize the parameters, and that can be done effectively through the support of some academic interventions. When we discuss about the fiber reinforced composites using the photopolymerization process, here as it's evident from the figure, there is a liquid resin, and this liquid resin is cured with the help of either UV light or with the help of lasers. In SLA, it is the UV light that is being usually supplied from the bottom. So this light will cure the resin. In the meantime, it is required to ensure that this composites, these fibers, be it continuous or be it chopped, come under the liquid layer to be cured. So if that is ensured, then we are able to generate a sound composite material with the help of this resin. And so here you may use the short fibers, very tiny size of fibers, or even continuous fibers. And there is a possibility to use a fabric of fiber, a fiber mat also, to create these fiber reinforced composites. However, their effectiveness and the quality and the strength have vast deviation, and there is a huge range of the property variation that we may observe depending on what type of fibers we are using. Usually there are two methods of preparing composite materials by SLA. The first one is by pre-mixing the reinforcement and resin together. So here there is a scope that we may mix the short fibers. The short fibers is mixed with the resin. So it can be tiny particles, or it can be in the almost powdered form, and that can be mixed with the resin, and with the resin it would flow, and the necessary curing would be carried out with the help of UV light. Sometimes we may not do that. We may not mix the resin and the fibers, but we may disperse the fiber once the layer is laid on the surface for curing. So in such cases, continuous fibers can also be placed, and it is also possible that such fiber mats, the fabric of fiber, that also can be laid. However, it is not that effective as the pre-mixing process is effective. So these are different ways in which composites can be created by the photopolymerization process. Thirdly, when we talk about the process, is the laminated object manufacturing process. Here the feedstock itself, the raw material itself for the process, is in the form of a sheet. So a roll of sheet is already put up on the spool, and it passes through the layer wherein some layer is passed upon, and each layer is cut as per the design. So it is in a way, it is like depositing those taking up the stacking of, say, papers. You have one piece of paper, and with the help of fevistick you fix another layer over it, and then third layer and fourth layer, and if you create the layer after layer of those papers, it would generate a 3D part. Similarly, here also the sheet is the sheet is cut into the desired form, and then that is how then the roll is wound on the waste side, and the new portion comes over it, and again the cutting takes place once it is fixed over it. So this is how this is being carried out. Now when we talk about the fiber reinforcement, then such type of sheet material already has a pre-peg sheet wherein the fibers are already previously reinforced. So here it is already mixed into it, and when the regular process takes place, we eventually generate a part which is composite in nature. However, the process is not that effective as the other processes, and so though theoretically this has been demonstrated, practically it is not that widely applicable and being utilized for certain applications. The final process that we can use for fabricating fiber reinforced composites is SLS process. Now we know that in case of SLS, we have the either the metal or the polymer powder, which is being cured with the help of a lesser source. So here in this case, some polymer is being used, polymer powder is being used, and very tiny particles of the fibers, very short fibers, which are almost in the powdered form, they are mixed with this polymer powder, polymer particles in certain proportions, say 1%, 2%, 5%, 10%, whatever you select for the study. Accordingly, these short fibers are mixed with this powder, and then this powder is usually sprayed on the layer, and it is being cured with the help of the laser source. So there is no much difference when you want to fabricate composites, fiber-based composites with the help of SLS process. Only thing is, here you cannot use continuous fibers, here you do not use fiber mats, but the fiber that you utilize has to be very short, very tiny, in the form of some powder. Usually the carbon fibers and glass fibers are being used as reinforcement with the SLS process, and the polystyrene or polyamide are the widely used materials as far as the SLS process is concerned. So this is how this process, these are four ways in which fiber reinforcement composites are being fabricated. Now I would concentrate on FDM based process, because this as on date has different ways of fabricating the composites. So as compared to the other three processes, there is a good variation in which the composites can be created. So there are four major variations which I will briefly discuss. First is we embed the fiber manually into the printed layers. So we layer after layer we put up the fibers by ourselves. We embed the fiber previously in the filament. So we make a filament, we extrude a filament with fibers mixed into it. The third way is embedding the fiber in the injector. So there would be a separate spool of fiber and a separate spool of the polymer, but when they pass through the nozzle, they pass together. So that is the strategy in this case. And finally, the process has the scope of embedding the fiber directly into the component. So it means that the fiber does not come into contact with the polymer in the nozzle. It comes out through a separate nozzle. It only comes into contact with the polymer when it is laid. So it comes directly in the printed part, in the component that is being printed. So these are four different ways in which this process can be carried out. The process means the FDM based 3D printing of composite can be carried out. The first, which I talked about, is embedding the fiber manually into the printed layers. So here what you initially do is you print first layer. Okay, so by usual method with the filament we print this one layer. Now when this is being done, after that we place the fibers on this surface. Okay, immediately after this is being printed, we may place continuous fibers, or we may spread short fibers, maybe in proper alignment or maybe in a unaligned fashion, whatever we wish to study. But we lay the fiber on this layer, which is right now mentioned as a lower plate, and before this layer gets fully solidified, this is being done. So once you set the carbon fibers, this particular case reported by Mori and his team talks about the carbon fibers. So I have borrowed the image from their paper. So this can be carbon fibers, but it can be other type of fibers also. Once these fibers are laid, once you see these fibers are laid, there is next layer which is being printed over it. So then the next layer of the polymer is put up. This is how it is being done. And then you can have multiple layers. One layer is for the polymer. Then you have one layer of fiber. Then you have another layer of polymer. Then you have one layer of fiber. Then you have another layer of polymer. This is being done. So here the usual 3D printer, simple 3D printer is being used, and the carbon fiber somehow is being laid on a recently printed layer so that it gets some sort of fitting into it well. Now the better experimental work which the team has reported is the effect of heat treatment. So once this part is printed, they put it in some oven and heated it for some time. And what was their observation? This was their observation. When you carry out heat treatment of these parts, proper thermal bonding takes place between the polymer and the carbon fiber. You can see over here in this first figure where there is no proper bonding. There was no heat treatment provided. So when you went under the effect of tensile testing, when this was being done, when the tensile testing was done, there was a breakage of the polymer, but the carbon fibers did not break. They came out from this portion. From this portion they came out, and they remain as it is. They did not break. So that is evident. If you see this portion, it is clear that only the polymer has broken and the fibers have remained intact. So at that point of place, the fibers did not break, only polymer break. And so the fibers came out from the other portion of the polymer. Now when proper thermal bonding is carried out, the heat treatment is provided, the bonding between the interlayers of the polymer along with the fibers is very good. So the layers, the two layers that we have, and when you have this fiber in between, these are the two layers, and if there is a fiber in between, because of the heat treatment later on, these layers also mixed very well with each other, and the fiber also got very well impregnated in these two layers, the one above and the one at the bottom. So that resulted into such a case where when the tensile testing is carried out, okay, when this is being broken, at that time it is found that along with the polymers, this can be seen over here, along with the polymers, you see the polymer also breaks and the fibers also break. The fiber did not come out from this portion. It is evident over here. So some sort of heat treatment at a temperature slightly higher than what is required for the polymer to be printed, then it is possible to create a sound and a strong bond. The values of the temperature and the strength difference that is obtained, that is reported by the researchers, but that was I felt not to include it in present discussion. The second process that we talk about is embedding the fiber prior to injection. It means what we do is we embed the fiber in the filament itself. So when you make the filament, you embed into it. So what you do is, here you have the polymer grains, the particles, and you mix the chopped fibers into it into certain proportion, and then you carry out the extrusion process. I'll discuss about this polymer extrusion when I talk about nano composites. This we have tried, but I would be discussing it in the next topic in this session. These fibers are mixed with the polymers and the composite filament is created. So now when you carry out the FDM process, it is the usual FDM process that you carry out. There is no difference, there is no requirement to worry about the fibers. Only problem, as I said initially, that can occur is the clogging of the nozzle. But that happens when the proportion of carbon fiber or any fiber in the filament is beyond certain value. So that may result into clogging. Not only that, clogging also occurs when nanoparticles are also mixed into it. So it's not, clogging is not a rare problem. It usually occurs when there is some mixing with the polymers. So this filament can be used to print the parts effectively. One very interesting result has been reported by Technell and his team, wherein what they did was they used ABS polymer and they mixed carbon fiber into it in the proportion of 0.3, that is 30% carbon they mixed into it, and they had some very interesting observations. The first and foremost thing that you see is when you are printing the neat ABS without mixing carbon fiber, when you print this neat ABS, you can see these are different rasters. So when this happens, the layers get deposited and they settle over each other, and once they solidify, some sort of void remains in between. Now this void that is found, okay, this void has a size of more than 100 microns. Okay, so that is the size of voids into this, and its specific strength is found to be at certain value. Okay, now as compared to this ABS, the aluminum 6061 has slightly larger value of specific strength. Now when 30% carbon fiber is embedded into the ABS polymer and the filament is used to print it, what you observe is this inter layer voids, the size of these voids drastically reduces. It becomes less than 30 microns. Okay, so there is an improvement in the way the parts are solidified together and voids are reduced. However, another important observation that comes up is in this, in a single layer. Say for example, if this is that layer that is printed and you have those chopped carbon fibers over here, then around these fibers there is very tiny amount of void, and the sum total of such voids all across these parts, you can see these are the fiber particles, and the small tiny voids all across the fiber particles, they exist throughout the part. These voids are between 4 different layers. However, here very tiny size of voids are generated all across the fiber. Now when you have such porous structure, when you have such voids, you naturally reduce the weight of the part. So when you compare the part with this neat polymer and one with this 30% carbon fiber, there was no major difference in the mass and volume of the part. However, the larger size of voids were reduced, and there was considerable increase in the strength of this part, better than what aluminum demonstrated. So carbon fiber based ABS gives you some strength which is better than what aluminum exhibits. So that is a very important observation reported by a research team. The third strategy that we can think of is embedding the fiber in the nozzle. So in this case, what we do is there is a single nozzle. Okay, you can see that there is a single nozzle. You have regular spool of this work is being reported by Lee et al., Lee and his team, and here they are using PLA as their polymer. So the filament of PLA is passed into the nozzle, and on the other side there is a bundle of carbon fiber. So carbon fiber is also passed into the nozzle. So the fiber and the PLA raw polymer, they come out through the nozzle simultaneously, and they get deposited on the layer, initially on the table, and then one over the other. So here what happens is you are able to use continuous fiber. So when that may not be the case in case of the previous two methods. However, here it is required that you use a continuous fiber, be it carbon fiber, be it glass fiber, but a continuous fiber has to be used and it has to be passed through the same nozzle. Now, often what you observe is that when you are using a polymer like ABS or PLA, after certain hours of use, the nozzles start getting clogged. Even with the regular polymers also, they start getting clogged. Now, when you try to pass a fiber along with this polymer through the nozzle, that clogging starts happening very fast. Okay, so if I'm just quoting any number, if the polymer works for say about 100 hours of time, the nozzle works for about 100 hours of time. So for pure PLA polymer, when you mix fibers into it, it may work 25 to 30 hours. So that would be the life of these nozzles would be drastically reduced. And so there has to be certain design changes in the nozzle, and its opening may be required to be slightly enlarged than what the standard size of 1.75 mm is concerned. So here this is what happens, and they have reported this to be working well. The part is able to get deposited, and however, what happens over here is when the polymer passes through the nozzle, the filament, the polymer filament, when it passes through the nozzle, the fiber is also pulled together. So once you just put it with the polymer which is slightly in the molten state, then along with the polymer the fiber is also pulled. So that is the extrusion process in this FDM itself helps to pull the fiber. However, to ensure that this pulling of the fiber with the polymer is continuous and proper, it is necessary to work on by trial and error. It is usually required to find the deposition speed and the layer thickness which can be generated, so that two things are achieved. Number one is proper passing of the polymer and the fiber filament together, and once they are deposited, proper solidification of both of the materials simultaneously. So that is something which is tricky. So in such a process where we want to embed the fiber through the nozzle, some sort of parametric optimization is required from machine to machine. Each and every machine has its distinct range of temperature, very small range of temperature where a particular polymer will work. Say for example, one machine is able to print only PLA in the range of 185 to 195 degrees Celsius. So if you try to go to 198 or 200 degrees Celsius, it may not work. If you try to go at 175 degrees Celsius, it may not work. There can be another machine which may work effectively from 170 to 185 degrees Celsius. So from machine to machine, certain trial has to be carried out initially to understand the temperature range through which this polymer, the selected specified polymer, is being printed effectively. It can pass the polymer, but once it gets deposited, it gets warped or the layers are separated. So if that happens, it means our strategy to print is not proper. The final method is embedding the fiber directly in the component. In this strategy, what you do is you have two separate nozzles. One nozzle works with the polymer filament. This particular figure is inspired by the work of ATAL, wherein they have used nylon filament. Here, this machine has two separate nozzles. From one nozzle you pass the nylon polymer, and from the other nozzle you pass the continuous fiber. Now it is very important to note that the part that you have modeled, the 3D model that you have created through the CAD software. There you have already defined how much polymer content you want and how much fiber content you want, and accordingly the machine will decide the printing strategy, the G code or M code or the program that it generates. That depends upon the proportion and the way in which you want to deposit the fiber inside this polymer. So accordingly the program would be generated, and layer by layer this would be printed up. More or less the process remains the same, but the strategy is slightly different. हेलो सर एक मेरा सेशन चल रहा है सर, मैं कॉल करता हूँ. Sorry for the short disturbance. Now in this case I will discuss our own experiments. A machine known as Mark II 3D printer is being commercially available through Markforged USA, and here what they do is they are able to print continuous fibers along with the polymers, and that would help us to print a composite. In this machine you can see that there are two different separate spools and separate nozzles. So the one is for the polymer and the one is for the fiber. So you can see that these are the outlets of the nozzle. Here this is a nozzle for polymer and this one is the nozzle for the fiber. It is possible to use three different types of fibers. One is the carbon fiber, the other is the Kevlar fiber, and the third one is the fiberglass, the glass fiber. The matrix material is a nylon filament which is commercially known as Onyx by the machine. The diameter of this nylon fiber, or you can say the diameter of the nozzle opening, is 1.75 mm, and the diameter of the fiber nozzle or the fiber filament is 0.3 mm. We have carried out work on the glass fiber as of now. Now I would like to go through the machine. I hope the streaming is going on well. This is the Markforged Mark II machine that we have in our lab. And the most important thing about this machine as compared to the other FDM printers is the the table. But right now we are seeing that there is XY coordinate movement along the Cartesian coordinate, and this is the feed mechanism. The larger size, the larger diameter is the one for the polymer, and the smaller diameter is for the fiber, and these are, both of them are fed together through separate nozzles. As you can see, these are the two nozzles. The larger one, the larger diameter is for the polymer, and the thinner diameter is for the fiber. Now, as I was saying, the most important part for this machine is its table. So the build platform can be separated. So usually that does not happen in case of the other machines. So this is a magnetic build platform. So that can be separated, and so once the part is printed, you can remove the platform and then easily you can remove the part from it. So that becomes easy. Often it so happens that when you are removing the part, it may get slightly bent, it may get slightly warped. You can see the spool for the filament is placed, and these are the two nozzles. The black one that you see is for the polymer, and the brass one that you see is for the fiber. So this is how this internal structure of the machine is. Now when you see the feed mechanism for the fiber, okay, the tricky issue is to pass the first end of the fiber through this system, feed mechanism. So here you have the spool and you have to pass the fiber through this feed mechanism till it reaches the feed mechanism where it is automatically pulled. That is slightly a tricky task, and sufficient care is required to be taken so that it does not break while the manual feeding that you carry out. Once that is fed into the mechanism, it effectively is passed and it is taken care of. The polymer is being fed through a separate spool, and that spool has to be taken care of in a dry box. It is generally required to place in the dry box because if the polymer absorbs some sort of humidity, if it absorbs humidity from the atmosphere, it loses its flexibility and often it starts getting brittle. So sufficient care has to be taken to preserve this polymer filament. As such, a half a kg of this polymer costs somewhere around 10,000 rupees, and the 300 grams of this fiber is also costing around 15,000 rupees. So in a way, this is a very costly process as far as the raw material is concerned. When in the next slide, when I talk about the software, we'll come to know that this is required. This machine is protected by the manufacturer in such a way that you do not use any another filament other than what they supply. There are certain process parameters which are possible to be varied, and we have tried to vary them. One is the orientation of deposition. So one can be the flat orientation. So you lay down the part on the table. The another orientation is on the long edge. So what you do is you lay this part on the longer side of this edge. Okay, so on this longer edge, you lay it down. And the third strategy is you use this shorter edge. So this is how you deposit it, and that gets deposited on the shorter edge. So this is how you do. There are these three different techniques. Recently, there are good number of publications which suggest that this does not work. This works well, and this also to certain extent works well. Over and above the orientation, the another the possible parameter is the pattern. You can have triangular pattern deposition for fiber as well as for the polymer. You can have hexagonal patterns. You can create hexagonal patterns, and you can create the rectangular patterns. Now these patterns are laid this way. This is how they are laid. Now it is interesting to know if you keep 100% density. Okay, so if you want to make solid part, then there is no fun in creating this type of designs. But when you go for lower density, say 50%, 70%, so what happens is there is if this is the part, and if you have decided to have 30% of the this is how the part gets deposited. I'm just trying to show. And rest of the space between the polymers, between the fibers remain vacant because you have ensured some smaller value of density. So these type of patterns work well when you need to reduce the density, and when you reduce the density, you reduce the consumption of material as well as you reduce the time for printing. And even if you in such situations also, with such lesser density also, you are able to get some better strength as compared to the other competitive materials. So if you see the isotropic fibers deposited on the rectangular pattern, then there is a possibility to change the orientation of these fibers. It can be 0 degree as seen over here, it can be 45 degree also, and it can be deposited at 90 degree also. Now these degrees are with respect to the deposition of the part that you decide. Further, it is also possible to define concentric fibers. Say for example, if you want to print a part like this, you may define that initially you want to have some concentric boundaries, maybe 1 or maybe 2 or maybe 3 or maybe 5. So that may help to increase your strength, and then accordingly if you have decided the triangular pattern, then this is how it gets deposited. So concentric fiber rings are also possible. So there are ways in which you can play with the pattern, you can play with the infill density so that you reduce the consumption and still try to increase the strength of the part. Now the Eiger is the software which is cloud-based slicing software being developed by this company. Now this is a cloud-based software, so you do not have it on your PC. You need to have proper internet connectivity when you want to fix up the design, when you want to fix up the parameters. So whatever you do, that gets entered. Just as you have emails in your inbox, this also remains in the inbox, and the company knows about it, what you are printing. So that is how, this is how they are trying to reduce the scope of using different materials over than what they have. But then there are ways in which people have been doing it. We being into research, so we maybe try to use the best possible components, so we cannot attempt for that. So there, the first thing that it showed is you can select the type of filament and type of fiber. Then you decide what level of density you want. You can also fix up what fill pattern you want to have. Then you also decide number of layers that you want to have of the polymers above and below the final fiber layers. You can also fix up the concentric circles that you want to have around as a boundary. And so those things, these are the things which you can define for a specific part. Now suppose if you have selected carbon fiber and you try to fill up the glass fiber, somehow the machine is able to recognize it, and it gives you the message that selected material is not present, so it does not allow you to move further. Then you can define the angle that you want, 0 degree, 45 or 90 degree. So these are different. When you make this selection, it gives you the part details, what dimensions you have, how much time it would take, how much it would cost you, what would be the mass of the final part, and what would be the amount of each material, the fiber and the polymer being used. Now when you have defined this, it also makes a suggestion that there are certain selections which are not as per their standard manual. So it gives you a warning that this selection can be slightly modified to improve it. However, if we want, we can we can follow those instructions, or we may decide to ignore them. So once that is done, we come across a part. Now this is what you see. Suppose there are 32 layers. Each and every layer you are able to see. Then what you can do is, if you want to make certain changes, you are also able to do that into a group of layers. Say for example, 15th to 20th layer, I want to change the concentric circles. Say from 3 I want to make it 4, or from 4 I want to make it 1, whatever I want. So whatever change I want, that can be done into this drawing. So right now the work is on 25th to 28th layer. Then you can see each and every layer, how there would be this gray color that you see is the polymer, and the golden color that you see is the fiber. So 29th, say 8th layer has more of fiber, 25th layer has half of fiber, and that is how it is being used. Now once you create the program, how do you print this part? I'll just try to skip through this. You need to select the program first, and whatever program that we have selected, that is being imported in the machine, and based on that, certain level of temperature for the nozzles as well as for the build platform is achieved initially. And once that is achieved, once the temperature is set, we can initiate on the printing. So first what happens is, the first layer, the first boundary is created, the outer periphery is created, so that it is known that the entire printing of the part would be carried out inside this. So in a way it sets its own Lakshman Rekha initially, and by that time it also checks whether the setup is properly placed or not. So in case if this outer ring is not printed properly, we come to know that we need to make change. So in a way, we don't initiate the printing of the part, and and ensure that we do not make any mistakes out of it. So that is being done. Now you can see that this part is being printed. At some point of time, you would be able to see the way in which the filament is also the fiber filament is also laid. Right now it is the polymer that is being laid. The black color is the polymer, and the white color would be the glass fiber. So this is how the part is being laid, and then this is how the fiber is being laid. Okay, in the isotropic way at 0°, and then you have selected the triangular pattern with say 50% of the infill density. So the entire structure is put up that way. Now you want to have a full layer at 45° for the filament. So that is how this layer is being printed. So then this is how it ends. So this part ends, and then you can separate the entire build form, and very easily you can remove the part. So the chances of any deformation in the part during this removal are greatly reduced, because as per your convenience you are able to remove it. So this is how the printing is carried out, and you can see the part that is printed. This is the drawing of one of the layer out of those 32. You can see that here you have this here, this golden color is the filament. You can see that filament, the glass fiber is being laid. Then you can see that wherever the space is there, okay, when there is short space available, everywhere the polymer is laid. So you can see this polymer is laid over here, over here, over here, over here. So throughout at all the places you can see, wherever there is opening in the drawing, it is shown that there is a polymer. So there also you can see the polymer is laid. So this is how very effectively both the materials are laid in a single layer through two different nozzles. We have initiated this task, and recently we are working on the tensile, flexural and impact testing. The primary test that we have carried out suggests that in the tensile testing, we tried to maintain 30%, overall 30% of the fiber volume fraction in the final component. And as per the ASTM standard, we tried to print it. And what we observed is, as compared to the single nylon polymer, when you mix two different grades of fiberglass, there is substantial rise in its strength. So from somewhere around 30, the strength almost becomes 4 times above 120, you can see. So different grades of fiberglass, when they are mixed, though there is no major difference into these two fiberglass, but as compared to neat polymer, there is a drastic rise in the strength. Now this probably is because of the type in which the fibers are laid. Now if you see that when you have only the polymer, then it results into larger strain and there is a ductile failure. Okay, but the strength that you may get is relatively less. However, in contrast, brittle type of fracture occurs in case of those polymers with the fiberglass, but you observe a sufficient rise in the strength before they fail. So the strength is very largely improved in case of the polymer with the glass fiber. These are some of the observations. Why you observe, what type of failure you observe, I'll not go into details because of the lack of time. Similarly, we carried out impact testing and we observed that there is substantial rise in the impact strength of the fibers. Say the strength was less than 100, and that almost increased to 5.5 times to 7.5 times. So there is a drastic increase in the impact strength also of the parts when you are mixing fiberglass into it. There are the reasons we have tried to see through the microstructure, but I'll avoid discussing it. There is an interesting case study using the same principle where a big area additive manufacturing system, which is developed by Oak Ridge National Laboratory along with Cincinnati, they have created a very large machine, and they are able to print very large scale sizes of different geometries with the carbon fiber reinforced polymer composites. So this is a single part rather than printing it separately and then and assembling those parts. This is a full scale aerospace trim part, and those that is being printed simultaneously into a single product. Another observation has been the successful story of a Local Motors, that is a US startup, where they have 3D printed the entire body of an electric car in a single go. So they have printed the entire body as a single part with the help of carbon fibers, and it is working well for them. The second type of process which I want to discuss is the polymer based nano composites. Now, in this case, when you talk about nano composites, you add certain nano materials like graphene, like CNT, like nano ceramic particles or metal nanoparticles. But most widely are the graphene and the CNT, carbon nanotubes, that are being done. We have also tried to attempt it with the help of graphene, because graphene is something that is finding very much attention because of its excellent electrical, mechanical and thermal properties. And almost three types, the FDM, the SLA and the SLS process, are able to use graphene for printing. We tried to create a nano composite, graphene based nano composite with the PLA filament. So what we did was we mixed them in certain proportion of 1 to 5%, and then we dried this and we fed it through the extruder, and we set the through various trial and errors, we set the parameters so that we could get the filament in the size of 1.75 mm, and this filament was generated at our own laboratory. So our department has this facility and we are able to print these filaments. We studied three different conditions, the 1%, the 3% and the 5% graphene PLA based extruded filament, and we found out some specific range and specific temperatures where this can be effectively printed. This worked well. However, we found that lower percentage of graphene gives better result as compared to the higher proportion as far as tensile and flexural strengths are concerned. This is an ongoing project, and so we are trying to work on this percentage concentration so that we find out something wherein it observes to be improving than the neat polymer. The the other thing that I wish to focus on is the polymer ceramic composites. Now, this is an interesting domain to work on. For various biomedical applications, we need materials that are biocompatible, which have very high corrosion resistance, and which are highly flexible. Otherwise, it is not possible to use them in any sort of biomedical applications. So here, various ceramics like titanium oxide, like zirconium oxide, like aluminum oxide, and certain calcium ceramics, these are being used as reinforcement with usually polyamide, polypropylene, and PLA. Now these are being used, they are being mixed with this in different ways, and certain structures for biomedical applications are generated. One such task has been reported by Jacques and his team, wherein they mixed ceramic powder hydroxyapatite with PCl, polycaprolactane, and they tried to create mimic the design of a human bone. Okay, so this bond that you see, they have tried to create, this is the portion which is being studied, and this is the part that is printed. You can see the level of flexibility under compression. It gets very easily compressed, so it is highly flexible, but when the load is removed, it regains its shape. So in a way, this becomes a very strong and a very flexible part. Not only that, you can also be able to feel the compression and the retraction with the help of just axial finger compression. And once that is being compressed, it again regains its original shape. So there is a good scope to work into the area of polymer ceramic composites. Not only this one particular application in biomedicine, there are applications in the casting molds, in case of MEMS, for the components like sensors and photonic crystals. You can see there are different 6 different conditions that you can see, wherein people have tried to fabricate silicon oxide with the help of photopolymerization process, where a scaffold is generated, certain photonic crystals are generated, a very micro turbine blade is printed, some impellers are printed, and even tiny investment casting parts are also printed. Now, when you try to print such small size, say this turbine blade or say impeller or some casting components in very small size with the polymers, when they are being used, when they come under the effect of certain loads, they immediately break. But when such ceramics are mixed into them, they gain better strength and they gain better properties like corrosion resistance and flexibility, because of which they find very good applications into the chosen field of application. However, one problem that we face is related to the nozzle. Usually when we try to use the smaller size of nozzles, it does not work. So the brass nozzles are usually used for polymers, but when you want to use ceramic particles along with these polymers, not only ceramic but even metal powder, if you want to use, then generally hardened steel is preferred. The nozzles from hardened steel is preferred as compared to the brass nozzles. Finally, I come to the discussion on polymer metal composites. Here, it is also a very promising field. In polymer metal composites, we use polymers, certain polymers as our base matrix, and we mix metal powder into certain proportion as a reinforcement. So what happens is, when we create such a composite, we are able to we are able to modify or improve the properties like adhesiveness, like flexibility, like conductivity, like processability, like toughness and strength. And this depends largely on different compositions of this metal powder into the base matrix of polymer. The easiest way of carrying out this process, as we saw in case of nano composites or in case of ceramic composites, is to mix these particles initially in the filament itself in certain proportion and then use the filament for the FDM printing. However, it is possible to a large extent to mix these metal powders well with the polymer powder and utilize it as an SLS process, or even mix them evenly with the resin and try to photo cure it. Now, what limitation comes up about the composition is that when you mix metal powders, the viscosity of this polymer, usually polymer has to flow through the nozzle. So the viscosity plays certain role in its partial melting that is required. But because of metal powder, this is compromised. Okay, so it is necessary to use different additives like surfactants and plasticizers along with these metal powders. So from the type of metal powder and the composition of metal powder, we may need different types of surfactants or plasticizers in different proportions, and there are no standard rules yet available. So there is a scope to work with some industry in defining the quantity of these additives along with the metal powder to generate a sound part and work on its flowability. These additives, when you mix up the surfactants and plasticizers, they decrease the viscosity and try to make it more homogeneous. Most type of metal powders which have been reported till now in last few years are aluminum or iron based powders, and usually the matrix material of ABS, polypropylene and polyamide is being used with these metal powders. It is possible to provide better thermal properties to the polymer matrix composite. So that can be done when you play with the size of these particles. So even deciding what size of the metal powder to be used, that also is an interesting area domain of research study. Now, when we compare 3D printing, especially the FDM process, over traditional manufacturing processes for composites, what we find is the manufacturing of the parts does not require the use of molds. Here you don't need to make any mold. Usually in the other process, whatever shape you want, that shape mold is required. Whereas in 3D printing, that time and the cost associated is totally eliminated. The other advantage is there is no scrap during the process. Okay, no scrap. Material wastage is almost close to zero. So that is also a gain. The other advantage and most prominent advantage with the part that you fabricate is that you require very few post treatments, and sometimes you don't need any sort of treatments. In case if you are going with the photopolymerization or SLS type of process, often you don't need to go for any sort of post processing or post treatment of these printed parts. So that is also a unique advantage of this process. Now when you design the part, for the designing of the model, you need to fix up. A human intervention is required. Everything else is totally automated. Entire process takes place by itself. You only need to see it from a position. So the chances of human mistakes in laying the matrix, in mixing the reinforcements, those things which may come due to human error are almost eliminated. So the part becomes the printed part is almost as per your required condition, and the chances of its failure because of some errors are largely reduced. However, one of the issue is that still you cannot go for mass production. This is a highly customized process, so you cannot go for mass production. Except FDM, other processes can go for some sort of mass production, but for FDM it is a tricky task. Now, what are the research scopes into it? These days we are seeing very high awareness and consciousness about taking care of the environment and carbon footprint. So there is a possibility to think about including natural fibers, not man-made fibers, but natural fibers, and try to print them along with the strength of these natural fibers is quite less than the man-made fibers, and so they may break during the process, and they break is what some researchers have reported. So that is a very big issue. But however, there is a potential in case if to some extent if we are able to reduce the man-made fibers and increase the involvement of natural fibers, then we may be able to create better composites which may be environmental friendly. So that is one aspect of the scope of work into any of these type of polymers composites. Still, there is a good scope to work on metal based polymer matrix, and there is no wide scale study being carried out. So its feasibility and its possibility to use it to increase various other properties other than the only the strength can be a good scope of research. Now, when we try to fabricate filament for FDM, there are good number of studies that have been done on various levels of polymer composites. But when we are mixing the nanoparticles like graphene or CNT, or nanoparticles of composites, or nanoparticles of metals, there is still a scope to work on. But very large scale research is being going on in different places. So in say few months or maybe 1 or 2 years of time, these research scopes will vanish. New research scopes will have to be thought of, but as on date, I feel that there is a scope to work into this area. These are few of the references which I have used into it. As you can see that our team works on FDM 3D printing, SLA 3D printing, CFRP, GFRP printing. We are also able to fabricate our own filaments. We blend different polymers to generate blended polymer filaments also, and we work on nanocomposites also. These are some of the tasks which our research scholars are right now working on. This is the contact detail of our team. You can now you already have contact details, so I need not, but many of these interesting videos of the student projects you can see on our Facebook page or on our YouTube page. So with this, I come to the end of our presentation. Thank you very much.